Alright, so this is the notes for 3.8 Newton's method. So Newton's method is a way to determine zeros of a function. So you are pretty good. You have a lot of algebra skills that will get you through this. So if you're given something like f of x is 3x squared minus 12x plus 9. If you're given this, you have algebra skills that would help you to find your zeros. So your zeros, of course, are when you are finding where this f would cross the x-axis. So that would be f of x equal to 0. You know that you would factor out a 3. You get x squared minus 4x plus 3. And then you would factor that further, or in Algebra 1, you also knew you could also use the quadratic formula. So either way, but you would get x minus 3, x minus 1 if you were factoring. And then you would know one of these two factors, or maybe both, have to equal 0. And so x minus 3, yes, that would equal 0 at x equals 3. And x minus 1 would be 0 when x equals 1. Okay, so you would go through that algebraic work and find, okay, I have two zeros. One's at x equals 3 and one is at x equals 1. Okay, and so you have those algebra skills to deal with problems like this. Okay, where your algebra fails you is if you are given something like this. 24x to the 5th plus 6x plus 10. Okay, if you're given that function, you would start out saying, okay, so I'm going to find my zeros, see if you can factor anything out. So of those three, I can factor out a 2. Okay, I can't factor out any x's since 10 doesn't have an x. So you could, but then you'd have 10 over x, which would make your life worse. So then 2, you'd have 12x to the 5th plus 3x plus 5. Okay, and then from here, we would either want to be able to factor, or our other option over here was the quadratic formula, but this is not a quadratic, so we can't use the quadratic formula. And we also don't know how to factor this guy. So at this point, we would be stuck. Okay, our algebra skills are not getting us any further for this function in finding its zeros. So what Newton's method helps us to find is zeros when we cannot find it in another algebraic way. So the way that Newton's method works is, you know that you want to find the zeros of this function. We know that graphically, if you have some squiggle, your zeros are these x values. Okay, so where that function crosses the x-axis. Okay, and so if we're looking for those values, Newton thought of it graphically. Well, I can find those values, I just need to approximate them. And so I have an illustration for you to see how he figured that out. So he has some squiggle. Okay, so he starts by saying, all right, well, I know that I cross the x-axis somewhere around here. So if I know that it's crossing somewhere, around like half, it's somewhere below 2, I definitely know that if this is kind of an inaccurate graph. So I have some sort of guess point. So he called it guess point is x1. Okay, so he says, okay, so I just grab something that's close. Okay, so his guess point, so say you say that your guess point, you are like really not confident about your graph, and you say, well, I know that it's like around the y-axis. He can maybe be around, somewhere between 1.5 and 2, like I'm not really sure, but it's like somewhere in this vicinity. Okay, so he has some guess point that's close-ish. Okay, so very, approximated. So he has this guess point. He's saying, okay, so I'm going to start somewhere. So I start at x1. And then he decides, well, if I take the tangent line there, okay, so we know how to find tangent lines. We would take the derivative, because we definitely have the f function. So we take the derivative, that would be our slope, okay, at a certain point. And then if you draw in that tangent line, he found, hey, if I draw that in and I follow that tangent line down to the x-axis, this is a closer guess. So now I'm getting closer. So that's good. I started over here with my x1. I drew a tangent line, and I got closer. Well, if I got closer, can't I just do this again? and then I'd get even closer. Okay, so now I put my first guess, and my guess could be fairly far off. It needs to be pretty close, but it doesn't need to be very accurate. So you start with your first guess, you go up to your graph, you draw a tangent line there. You'll get closer. Okay, now we're going to repeat that process. Now we have this x2. Okay, we draw it up, tangent line. And then now we have this green tangent line. Okay, so now this green tangent line, it's even closer. Look how close it got. It looks actually like it's right on there. So we did it again. So we say, okay, well, this one was closer, the one on the red tangent line. So then let's repeat the process. Let's go up again and find that tangent line. So then that tangent line is even closer. So we might be pretty close at this point, but just to make sure that we are like right on that 0, we can do that again. So now we use this as our next x. Okay, so we had an x1, we have an x2, now we're going to use this guy as x3. Okay, so we're going to do that process again, make another tangent line. And at that point, we should be pretty darn close to what the actual root is. So now we have that point, and now we have this orange tangent line that went right through there. Okay, so then that orange tangent line gives us the last point. Okay, and so now at this point, like, we are very, very close. So we started off pretty far away. We had this x1, went up to our graph, made a tangent line. We got closer. It's not very close, but closer. Okay, so then we did it again. Took this point, went up to our graph, made a tangent line, and then we got close. Then just to be sure, we did it one more time. So we took this as our point where our tangent crossed the x-axis, went up, did another tangent line, which is this orange one. Okay, and now we can see, yep, that is going very, very close. If not equal to the root, that is very close to the root of our graph. Okay, so this part is outlined on your notes as well. So taking those x1 and then x2 and then x3 and finding something that is close to the root. So we are approximating the root, and the idea is that we're getting really, really close to the root. We still might be approximate, but we are very, very close to it. Okay? So that's the process. So you keep taking these x's, you keep going up to your graph, find a tangent line. Use that now as your x, where that tangent line crossed the x-axis. Now you go up, find your tangent line, you're closer. So you keep repeating that process. So in order to do that, we kind of need to go through how would we actually find a tangent line. So if we start with this x1, we went up here, and we said, okay, we want the tangent line to this graph. Well, to make a line in good old Algebra 1, you need a slope and a point, right? So we know, well, this is our point, x1, comma, f of x1, if we want to just keep it generic. And then we also need a slope, where the slope is going to be the derivative at that point. So we have a point, and then our slope is going to be the derivative of x1, so f prime of x1. So then if we have a slope and we have a point, we are good to go. We can find this tangent line. And then to find that point here, we would just need to solve for our x2. Okay, so it is in Algebra 1, you know, we wouldn't do this so abstractly in Algebra 1, but if you are given a point and you have a slope, you can find a line. So we're going to go through kind of what that process would look like. So we are starting, okay, how can we find our x2? So we started with our guess point x1. Okay, and so you should have this worksheet. So we had this graphic, okay, and we're saying, okay, so we started at this x1, we went up to the graph of it, and then we found our tangent there. Okay, and so our first tangent was this one along our x1. Okay, so that was our first tangent that we found. And then we said, hey, look, it hit the x-axis there, which is like pretty good. It's much closer than we were before. We started out over here. Okay, so then that was much closer, and then we said, well, okay, so now let's find how we would actually, discover what that number was. So we'll do it just generically, because then if we have just the generic x1 and f of x1, we can find it for all values. So we'll go through kind of how that would look. So if we are starting out, we have f of x. Okay, so things that we would be given. Okay, so we would be given f of x, and we would have a guess of the 0 or the root. Okay, and we'll just call him x1. So we're guessing that, you know, our root is around there. Okay, so you may be close, you may not be very close, but you need to be approximate. Okay, so to find the tangent line to a curve, we need slope and we need a point. Okay, so we're up here with our curve, so our point is x1, comma, f of x1. Okay, so that's our point. And then our slope is going to be the derivative value at that point x1. So our slope is f prime of x1. Okay, so now you put that into your point slope form. So your y minus your y. So your y value is this value. So y minus f of x1 equals, and then your slope, okay, and your slope is f prime of x1 times, and so is your slope times x minus your x value. So x minus, and that was our slope, that one's our point, right? So our x minus x1. Okay, so now that is our line. Okay, so that would be the equation of this pink highlighted line. Okay, but we don't want to stop there. I mean, that's helpful, but we need to find where that x2 is. We want that value. Okay, so we need to find out what that means. So x2, that coordinate there is our 0 for that line, and so that line crosses the x-axis, right? So there's your x-axis. Okay, so it's crossing there, which means your x2, comma 0, right? That's that point there. So if we want to solve for what x2 would be, we just need to plug that into our equation. So we want to find what is our line at x2, 0. So you just plug that in. So your y value here is 0. So 0 minus f of x1 equals the derivative of x1 times, who's your x value? Your x value that we're plugging in is x2. And minus x1. Okay, and again, our whole goal, we want to find what is that value x2, so we want to isolate that x2. So you just kind of do all your algebra. So opposite of f of x1, if you distribute this guy, okay, remember that that is going to be a number, right? The derivative at a point is a number, not a function. So we get x2 times the derivative at x1 minus x1 times the derivative of x1. That's just distributing. Okay, we want x2 by itself, right? So let's move this over here. Let's move this guy to the right. So we're going to have negative x2 f prime of x1 equals, okay, move the other guy over. So we still have this term over here. Okay, that guy went to the left, so this guy needs to come to the right, so you add it to both sides, right? So then you say plus f of x1. Okay, so that was just moving things around. Okay, again, we're looking for x2, right? We want that value, because we're saying, hey, it's pretty close to our root. What is that value? So then we need this guy by himself, so our last step is to divide all three sides by the derivative at x1. Okay, so then when you divide everyone, some things cancel to 1, so those would cancel to 1, so you would just have negative x1, and this one, nothing cancels because this is the actual function, this is the derivative value. Okay, so then over here, this cancels to 1, so you would get that negative x2, or the opposite of x2, so let's get rid of that opposite. So divide everyone by -1 as well. So if you divide everyone by -1, you would get x2 equals, that would now be positive, so x1, this would now be negative because we divided by -1, minus f of x1 over f prime of x1. Okay, so that is very abstract. So we're just going through, the most abstract example so that we can apply it to every example we have. But if we have started at some guess point, we've come up, we've drawn the tangent line. That was this point. Okay, so the actual tangent line formula was this, which would correspond to this pink line here. This is the equation of that line. But then we didn't want to stop at just the equation. I mean, that was fun, but that's not helpful. So we want the actual root value. So we wanted x2. So then we had to plug in that point, x2 comma 0, to actually solve for it. So now we know whenever you want that root of your tangent line, this is how you could find it. So you take your first initial guess, you subtract the value of the function, and then divide by the value of the derivative. Okay, and that is Newton's method. Okay, so that's how this came about. It was not, magic. That is how this happened. So Newton's method for approximating zeros is written out here. So you would say, okay, so there is a 0. You take f of c and you get 0. That means you cross the x-axis at c. Okay, f needs to be differentiable. Okay, and of course it needs to be differentiable because you're going to be taking the derivative, so it better work. Okay, you make an initial estimate x1. Okay, that is close to c. So close is a very ambiguous word. So, close. That's close. Okay, so you make an x1 that's close. Most of the time that is given to you. The initial guess is usually given to you, unless you're given the graph of the function, and then you start with your own guess. Okay, then you would determine a new approximation by using this formula. So we have x2 and x1. They made it even more generic. Your xn plus 1, and then your xn. So if this was x3, this would be x2. If this is x5, this is x4. So they're saying take which one you want, look at the one before him. Okay, so this one is x2, so then we use the one before him, x1. Okay, and you plug it in. So you have your value minus your function value over your derivative value. Okay, and so that is a very important thing to remember. So I don't want you to think that it's just this magical little formula that came about and Newton gave it to us, and thank goodness for Newton because we can't think for ourselves. But this is where it came from. Okay, so you can always derive it again if you forget Newton's method by going through your algebra. So you've set up your equation, you plug in x2 comma 0, you'll get there. Okay, so it's a little bit more efficient to have it memorized, but if you forget it, not all is lost. Okay, you can always go back through and figure it out. So you have this guy. And then the last part is you want to see that your first and your second, or this again is just n and then n plus 1. So it's your first and your second, or your third and your fourth. You subtract your two values and see if you're in the desired accuracy. So we'll go through what that means when we do an example. Okay, but so you keep repeating this method until you get to an approximated 0 that's close enough for what you care about. So this one, okay, we started with x1, we made our tangent line, we're like, yeah, he's close, but we didn't want to stop there because it's not that close. It's closer, but it's not great. So then we went up again, we made another tangent line, and so our other tangent line is an even better approximation, right? So we went up here, and so we have this approximation as well, and so we realized, hey, that's better. So you just keep going until you have a really good approximation. Okay, so let's do this first example. Okay, so we're going to use Newton's method to approximate a 0. So for this one, we do know how to find this using our algebra method, so I want us to see that we can use Newton's method and we actually get the 0 that we know is true. All right, so in order to calculate this using Newton's method, it tells us to calculate 3 iterations. So we know Newton's method, we need an initial guess. They gave us an initial guess. They said use x1 equal to 1 as your initial guess. So we say, okay, great. x1 is 1. Okay. Then to find x2, we know from Newton's method either here or over here, okay, whichever one makes you happier. So your x2 is going to be your x1 minus your function value at x1 over your derivative value at x1. Okay, and so we know, since we were given, that our f is x squared minus 2. Okay, so our f prime is 2x, right? So we just plug that in. So our x1 was who? He was 1. So we say, fantastic, it's 1 minus, our f is x squared minus 2. So you just plug it in. 1 squared minus 2. And then over your derivative of that value. Our derivative is 2x. So it's 2 times, who's our x? He's x1, he's 1. Okay, so then you're 1 minus 1 squared minus 1, and then over 2 times 1. Okay, so you're 1 squared minus your 2, so you're 1 minus 2, you're neg 1, all over 2. So then you're 1 plus a half, so you're 3 halves. Okay, so that's our x2. So we started out guessing that our root was 1. Well, we found out, oh, not really. He's actually closer to 1.5. Okay, that's equal. So now let's do it again. Okay, so we've done one iteration. So that's one iteration. Okay, so now let's do our second iteration. So x3, same idea, but now it's x2 minus f at that value, derivative at that value. So x2 was 1.5. So now, same idea, you're just now using your 1.5. So your 1.5 minus 1.5 squared minus 2 times 1.5. Okay? When you evaluate that, you'll get 1.417. Okay, so our first initial guess was 1. Then we realized, oh, it's actually closer to 1.5 maybe. Oh, now we know, oh, it's actually closer to 1.4. So now let's do it one more time and see if we get an even more accurate answer. So now x4, we use our x3 minus f of x3, derivative of x3. Okay, so our x3 was 1.417. 1.417 minus our function value. So our function is x squared minus 2. Just plug it in. X squared minus 2 all over your derivative value. Your derivative is 2x. So 2 and then x. Okay, and then you plug that into your calc and you get 1.414. Okay, so that's 3 iterations. So 1, 2, 3. Okay, so we found that actually our approximated 0 is getting closer to 1.4. Okay, so they told us to do 3 iterations, so we can stop there because they told us exactly how many they wanted us to do. So then we would say, fantastic, an approximated 0 of f of x is 1.414. Okay? And so we know how to actually find this one, right? You could do this with algebra. You don't need this. You don't need Newton's method. I just want to show you that it does work. So if we were trying to find the 0 of this guy, you wouldn't do Newton's method unless someone told you you had to. You would just set this guy equal to 0, right? And you say x squared minus 2. You would add 2 to both sides. So you say 2 is x squared. You would square root both sides, and you get the square root of 2 is the absolute value of x. Okay? And so you would know that x was plus or minus rad 2. Okay, and so yeah, we found the positive root. Okay, because we started at 1, we found the positive root. Okay, and that's an approximation for radical 2. All right, so that is Newton's method. Okay, we can automatize this using our calculator. So we can find it this way, okay, and we can have our calculator do all of this for us by setting this up in the initial time and then just plugging in each of our iterations. Okay, so that's how we'll practice the second one. But this is how you would find this. So you start with your first initial guess. You go through the process of newtons, so you just plug it in to here or here, whichever one is happier for you to memorize. Okay, and so you take the value minus the function value over the derivative value. So you're just plugging things in and getting a new number. Then, ta-da, this is your new number, and you do that with the next line. So then now this 1.5 goes to the next line. Plug him in, you get a new one. Now this guy is your new guy, so then he goes to the next one. So you're just using your numbers over and over, okay, until you are done with whatever accuracy they asked for. So they said 3 iterations, so we did 3, and we're done. Okay? It's very important that you say approximated 0, okay, because of course we don't know if this is an exact, how many decimal places it's exact. We know the exact answer is the square root of 2, which, is not this. This would not end if you were the square root of 2, because he's irrational. Okay, so let's do example 2. Okay, so using Newton's method to approximate the zeros of this cubic. So let's do this in our calculator so you see how you can be more efficient. So we know that our f is 2x cubed plus x squared minus x plus 1. We know that our derivative is 6x squared plus 2x minus 1. So instead of plugging this in every single time with new numbers, I can just put in generic. I know that Newton's method is my x value minus my f of x value over my derivative x value, right? So the way that you can do this in your calculator is putting it into your function. Okay, so go to your y equals. So here, go to your y equals. And we're going to put that in. So it's your x value minus your function value, which here is this. So you say x minus my function value. I'm going to make it into a fraction. Okay, so my top is my f over my derivative. So my f is 2x cubed plus x squared minus x plus 1. Okay, my derivative value, which is my denominator, is 6x squared plus 2x minus 1. Okay, so I'm going to make my calculator do the work for me. Okay, so I want to be able to plug in a few different things. They told me that my guess should be negative 1.2. Okay, so I need to tell my calculator to start at negative 1.2. So there's a few different ways you could do this. I'm going to show you using your table. So if you go to your second window, you'll get to your table set. I want to be able to tell it where to go, so I don't want it on auto. Do make sure it's on ask. Okay, I want to be able to tell it start at negative 1.2. Okay, so make sure it says ask, and then go to your table. Okay, and you might have stuff in there from before. If that bugs you, you can just delete it just by pushing your delete. So I know I want to start at negative 1.2. So let's say negative 1.2. Start there. Okay, fantastic. So now all I need to do is just keep track of what I'm doing. So I have my initial guess is negative 1.2. What did I get? I got that my second is negative 1.235. Okay, so that's my x2. Okay, so then how do I find my x3? Who do I need to plug in? I need to plug in to find x3. I plug in x2. Right? So now I plug in x2. So negative 1.235. Okay, so then, hey, there's my x3. Negative 1.234. Ooh, it's getting closer. Okay. So now I'm going to go in one more time. So that's my x3. So let's plug that in, negative 1.234. Okay, so then my x4 is negative 1.235. 4. Okay, and so it's saying, I don't know when to stop, right? It didn't tell me how many iterations. So instead of telling me how many, it just said continue iterations until 2 successive approximations, okay, successive means in a row, right? So 2 in a row differ by less than 0.0001. So it's accurate to that decimal place. So I just need to make sure, okay, am I accurate? Yes, I'm going down to 1.234. Okay, so then I know if that's my decimal place. This is not actually not enough decimals. So if you need to play around with it, you can try it. Oops, you can try it again. Well, that's what his graphs look like. So you can play around with it and realize, okay, so here I am. I know that I have enough decimals, and I know that it's the same here. So I would know my approximated 0 for my f of x is negative 1.234. Okay, so that's how you can do this very efficiently in your calculator. So just make sure that you are very careful with your y equals, that your x minus your function over your derivative. Okay, so go ahead and try example 3 on your own. So pause the video and try it on your own. Okay, and then check back to see that you did this correctly. So following, your efficient way to do this with your calculator, plug it in, find your answers, and then check back. Okay, so hopefully you paused this so you can have tried it on your own. So what you should have done is that you had your f of x is this cubic, so x cubed minus 2x minus 2, okay? And then my derivative is 3x squared minus 2. Okay, so then in my y equals, I know I have x minus my function value over my derivative value. Okay, so I have x minus, okay, I have my function value is x cubed minus 2x minus 2. My derivative is 3x squared minus 2. So I go to my table. Okay, I know my initial guess was 1.5. So I start with 1.5. Okay, when I have my initial guess of 1.5, my x2, okay, came out as 1.8421. Okay, I'm just going to delete these so you don't get confused. Okay, then for my x3, I need to use that value. So now I plug in 1.8421. And now I know my x3 is 1.7728. Okay, now plug that one in. How far do we need to go? We need to be to 4 decimal places, so it needs to be even to 4. So these are definitely not close yet. Okay, so now let's plug that one in. So 1.7728. So my x4, 693. Okay, we're getting closer. Okay, at least you're not fluctuating hugely anymore. You went from 1.5 to 1.8. So let's keep going. So now plug that one in order to find your x5. Okay, so now you got 1.7693. Okay, so now that we're at x5, so we look good. So we have 1.7693, 1.7693. So to 4 decimal places, so 1, 2, 3, 4. Okay, you can do it one more time if you are worried that this 3 might get bumped up to a 4. You can do that again. So 1.7693, and you find, no, you're still staying. So we look pretty good. So he's accurate. So we would say our approximated 0 of, and this one's not f, so let's write out our actual x cubed minus 2x minus 2 is 1.7693. Okay, so that's Newton's method. So make sure that you are working on your homework now. Okay, so follow through. If you need to, come back and rewatch any of the strokes on the calculator or any of these examples. But make sure you're done with your homework by the end of the period.